coefficients in front here are not really correlated. Another possibility could be that's actually not a fundamental scalar, but a bound state combined with or mixed with a Goldstone boson or pseudo Goldstone boson. Oops. So, but as I already had heard yesterday in the talk by Shaposhnikov as well, QC actually breaks electric symmetry. Let's forget it for the moment being about the business that the top mass is close to its critical value concerning the symmetry breaking. Let's take in a moment only the first or maybe in addition the second generation. Because then we would have a symmetry, let's take the first one, SU2 left times SU2 right. It's a global symmetry, we forget about electromagnetic interactions, weak interactions. At QCD scale, we would have condensation. And of course, this condensate is of the order 200 MeV to the power cube. And this condensate breaks the SU2 left times SU2R to the SU2 diagonal custodian. And this implies you would have 3 number Goldstone bosons, the pions. What would be, if this were the true model, the consequences? Well, we would have vector boson masses in the order of 100 MeV, not GeV, which of course is absolutely wrong. There would be no Higgs at the mass scale of MW or MZ. They would actually have equal masses, the vector bosons. The U1 electromagnetic would be equal to the U1 hypercharge, and a priori there would be no masses for quarks or leptons, but those you could induce via high-dimensional operators, dimension 4 operators. That works in principle. Of course, experimentally, this class of models would be excluded. We know the vector boson masses have 100 GeV masses. So now to say, okay, you're off by several orders of magnitude, forget about the model. As model builder, well, as I am, you start to think, and of course, as field theories, you see, okay, that's an interesting effect. So let's use this effect and come to the what's called minimal composite Higgs models. You can find nice overviews in those 2 references here. And let's assume for the moment being, beside the SU3 color times SU2 left times the U1 hypercharge, there's a 4th gauge interaction, which is strongly interacting, but gets asymptotically free at very high scales. And we will call this hypercolor in the following. There will be new quarks. I will sometimes call them hyperquarks in connection with the hypercolor here. And if I switch off all the standard model interactions, like gauge couplings, Yukawa couplings, you would find there's a global symmetry in this strong sector at energies above confinement. At some scale, there would be confinement. You would get the subgroup H1 of G. What it is as a need from a phenomenological point of view, we have to have the H0, the standard model electric gauge group. In principle, only the overlap needs to be an unbroken gauge group like the U1 electromagnetic, but of course this could be a subgroup of the H1 itself. So I'm just drawing here the more general case, but this should include as the H0 is a subgroup of the H1. And then of course the question is, what are the smallest group which can give electroweak symmetry breaking and a Higgs boson? And there it turns out that's SO5 times a U1X. The second factor, essentially, you need to get the hypercharges of the quarks correctly. Otherwise, if you were to only look into leptons, you could forget about this factor as well. The H1 would be SO4, so you break the SO5 by the condensate to SO4, you would still have the U1X. And this SO4 factor, as well known, corresponds to SU2 left times SU2 right, which is the custodial group of the standard model. Of course, the H0, as we need it here, is the SU2 left times U1 hypercharge, and the common group is the U1 electromagnetic. Breaking of SON to SON minus 1 is well known. This gives you n minus 1 Goldstone bosons. In this case, we get 4 number Goldstone bosons, which sit in the 2-2 representation of SU2 left times SU2R. The hypercharge is the third generator of the SU2R and the one coming from the U1X. And as I said before, this we need to get correctly the fermion masses. So how do we describe these things, and how can we eventually see deviations from standard model expectations? Simply let me sketch here. That's essentially what we do in chiral perturbation theory. It's the same formalism. So we have here the vacuum state. We have here the fields, the Goldstone bosons included. The vacuum state I denote here by one value in the fifth direction. That's my choice. That's not given, but I can always choose this basis. These are the broken generators times the Goldstone boson fields. And the sigma you can work out in the SON case easily. You will find that this has this form here. So this exponentiation is relatively trivial. It's a nice exercise for students to do that. And then when you want to include gauge interactions, you have to, of course, to use here the covariant derivatives, but then you gauge only a part of the remaining group, namely the SU2 left times U1 hypercharge eventually. You can formally include the complete SU2 right, and then send some of the states to very large masses to get the proper limit. As this works in both ways. When we then include electroweak symmetry breaking, what we do get is an effective Lagrangian of this form here. So, of course, what we need, that's what we have from essentially standard model structure. We have here the WEF plus the Higgs field times the combination of the gauge fields that we need in the standard model. If you do this more precisely, take into account all these parts here, the sine and the cos, cotangents, hyperbolicals here, we actually find, yes, that's 1 plus this part here of the mass terms. And then we have here, instead of what you would have in the standard model, factor 2, we would have a factor squared 1 over minus xi here. We have here 1 minus 2 xi's here, and the xi is the WEF of the Higgs boson over the decay constant appearing here from the spontaneous symmetry breaking in the composite sector. Experiments tells us, okay, this quantity has to be small. This can be at most, let's say, order 0.1, should be smaller, if one takes into account the latest results. But this gives an idea that this is a rather small quantity, and that this F has to be at a relatively high scale. So this would correspond to the pion decay constant in chiral symmetry breaking. Of course, we have fermions. We would like to have some means, at least, to explain why is the top mass so much higher than the other quark mass or fermion masses that we observe in the standard model. But these people have invented already several years ago this idea of partial compositeness. So the challenge is the Higgs transforms nonlinearly under G, because in the representation of G over H within the H subgroup, and there are no Yukawa interactions provided that the standard model fermions should be elementary, so should be realized linearly within the symmetry. So the basic idea is you take the elementary fermions that we have in the standard model, you put them in incomplete representation of your group G, so the global group. This, of course, amounts to an explicit breaking of the group, because I set behind certain components to 0, which in a complete representation would not be 0. And then you can put the composite fermions, so these are bound states of the hyperquarks. In this case, in this type of representation, these numbers here simply indicate those are the charges of the new states that you would expect. The D and du would have the same charges as D and up quarks in the standard model, so I did not put them here in addition. The delta here simply means that's a right-hand state compared to this, which are SU2 left states. And then you would get mixing between the standard model fermions and these hyperbaryons here, these heavy states here. And then you can say, okay, the top quark is those which is the linear combination of standard model fields which couples to these states here. Because if there's only one generation, let's do it for simplicity, you can always make a basis rotation among the standard model fields. Only a linear combination couples to those fields here. And in this way, you can say you can get the large Yukawa couplings or large mass of the third generation via mixing with these new states here. So that's the basic idea behind it. Of course, if this were simply spontaneous symmetry breaking, we would have Goldstone bosons, they would be massless. That's not what we observe, so we need a Higgs potential. But there we actually have two sources. One is what I mentioned just before. We have this incomplete standard model representation. This amounts in an explicit symmetry breaking. This gives rise to a potential. And then, of course, we only gauge a subgroup of the G over H. So the H1 is only a subgroup gauged. This is another explicit symmetry breaking. And in this way, you can get via contributions of this type here, Higgs potential. In the minimum model, you can do, or let's say estimate what they should look like. You get those two factors, and you find that there's a minimum indeed, which is given, a moment, that's at psi, as which is psi squared over V over F here. It's simply doing the math here. And then you essentially have a model which is working in principle, but of course, it's not quite generic because it is really the minimum model that works in principle. So what's now the generic setup? Because this would be an effective description, but eventually would have a more complete picture. I'm just outlining this here to give the rough idea. So the idea is at the scale, which I call here lambda capital HC, which is of the order of a few TeV. This will be the mass scale of the bound states, like in QCD, the proton is typically the mass scale of the bound states that we have in QCD. If we go up to higher energies, this new force here will become asymptotically free. That's not absolutely required. It's sufficient to get it running to a fixed point, but having that was asymptotically free simplifies life. And then in this case here, we have the condensation. We generate, oh, there's something missing here. There should be a small h here in. Sorry for that. The Higgs field with the physical state inside. We can have a spectrum of this type here. This will say big the price to pay. We get additional states, which of course is not really a price. This is what we can hunt for and see. Thanks. What this model would look like, but which realization is clearly given in nature. So of course, we have to have the Higgs boson at around 125 GeV. This does not exclude that there are additional light scalars. So several of these models predict actually light scalars in the order, let's say, roughly speaking, a few GeV, let's say up to 20 GeV, which decay dominantly into photons and gluons. And they would have escaped detection essentially, because at lab they would be electroweak singlets, you would not see them, only via very tiny mixing with the standard model Higgs. At the LHC, would have the production where two gluons into this S channel going to two photons, but at this mass scale, you're swamped by the background. There's no way to get this out with the current information. We'll have additional generic pseudoscalar number Goldstone boson, which means an extended scalar sector. And of course, as I just indicated before, you will have deviations in the Higgs couplings, which we measure currently at the LHC, and potentially at future colliders like an E plus and minus machine. So people have to think, okay, what would you really like to have from such a more complete model? So, of course, it should not contain elementary scalars. Maybe at some very high scale, let's say Planck scale, dot scale, you might have something like supersymmetry protecting the scalar masses at this very high scale. It's not excluded by this. And people like Sanino and Cacciapaio have constructed such model, where at the very high scale, indeed, you do have additional fundamental scalars protected by supersymmetry. You should have, to simplify life, a simple hypercolor group. You should have clearly a Higgs state among your pseudo-number Goldstone boson. A top partner amongst the top bound states that's desirable. It's not absolutely required, but it simplifies life for the phenomenology. And of course, you should have some consistency conditions to standard, like you should avoid anomalies. Asymptotic freedom already mentioned simplifies life. So there have been a flatter of models. I will show you in a second a slide giving a few of them. Let me just already mention a few generic features. So they all predict pseudo-number Goldstone beyond what we have in the Higgs multiplet. It's quite generic. And all these models contain several top partners. What I mean by top partners are spin 1/2 states, which reside in the same multiplet as those states which have the same quantum numbers as the top quark. In this paper here, they have given an overview of what they call minimal composite Higgs models and their UV completions. The word minimal can always be debated, therefore I put it here under quotes. I will take out one particular model here, this is what they denoted by M5 here, which has an SP4 gauge group. We have 5 hypercolors in the asymmetric dimension, the asymmetric representation of this gauge group, and 6 in the fundamental. So usually you need 2 different types of hyperquarks, because eventually would also like not to include the electroweak gauge group, but also the strong gauge couplings in this way. And that's where the fun starts from the phenomenological point of view. Let me take out this part here. I just said we have here the SP4. The global group would be SU5 cross SU6. This gets spontaneously broken via condensation of both the psi field and the chi field here. So both of them condensate independently. One breaks the SU5, the other one breaks the SU6, and we get as resulting subgroup at this level an SO5 cross SP6. The SO5 contains the SO4 subgroup, and therefore the electroweak part. The SP6 contains SU3 color as a subgroup. So there we can model the strong gauge couplings, which are still small compared to the new gauge quantum number, to the new gauge forces. The breaking here, SO5 to SO5, gives you a 14-plet in SO5 for the pseudo-number Goldstone bosons. If you decompose those into SU2 left times SU2 right, you find a singlet, a bi-doublet, which corresponds to the Higgs, and a bi-triplet. If you really take the electric charges into account after electroweak symmetry breaking, you get those states here. This looks very much like the Marchek-Wong model. However, the parity of this bi-triplet is opposite to the Marchek-Wong model, so it has a different phenomenology. In the strong sector, the SP6, as I mentioned before, has the SO3 color. I include here the U1 electromagnetic. There's actually an additional U1 factor that I did not write here explicitly, which gives rise to colored triplets and a color octet. In the fermionic states, we have SO2 doublets. We have colored triplets with different hypercharges, giving rise to, for example, a charge 5/3 state. But we also have a color octet, which comes as an SU2 doublet. And then, of course, we have a state corresponding to the right-hand dot quarks and a color octet, which is an SU2 singlet. This looks very much like a gluino in supersymmetric, therefore, this choice of letters. This would be, so to speak, a gluino in an SU2 representation in addition. So we'd have a charged color octet in a fermionic state, which is quite unusual. And then you would have here electroweak states. This would correspond to Higgs-Sinus and SUSY models, and this to the Bino. We will now present results for a very specific scenario. One can show in this model that if one takes the gauge part as it's known for this modeling here, this hypercolor, then it can have an accidental symmetry which would lead that one of the states is stable, which we assume is this Bino-like state here. Of course, in a more complete picture, this might be broken. We don't know, but at least at this level, that's possible. We assume that the fermions within an SU5 times SP6 representation are essentially mass degenerate. This works very well as long as the hyperquarks have the same masses. It might be different if those have different masses. And then all the mass splittings comes via the gauge interactions. And you usually give mass splits in the order of a few GeV up to a few tens of GeV, depending on the interactions. What you see, this implies that in this case, the color octets here have the largest cross sections at the LHC. This particle is stable, so we have large missing energy, like the supersymmetry. The electroweak states will be almost degenerate, so the Higgsino-like states will decay into pions and this Bino-like state, but with very soft pions. That's also a feature known in specific SUSY scenario. And for the pseudo-number Goldstone bosons, the pi8, the octet, can decay into 2 gluons, while the Westermino-Wittner term, top anti-top is possible, as the case in the first two, in the lighter quarks is possible. We neglect them here because usually they are small. If this decay here is not possible, because actually that's a baryon which should be lighter than pseudo-number Goldstone bosons, that's debatable. That's an assumption here. If this were not the case, we would have, for example, the case in the top and the neutrino, which corresponds to the scenario that this particle here is massless. So most of the things would still hold. Apart from here, you would have not soft baryons, but you would have 3-pi decays, including electric gauge bosons. So this would be the main change. So one can get bounds on these guys here. This is essentially like a stop right in SUSY searches is of order 1.3 TeV. The by 8 also has a bound of about 1 TeV. The signatures would be you have multi-top plus multi-jet plus missing energy. You can have a couple of soft baryons, but they don't count. What we did, we recasted SUSY searches. We use for this math analysis and checkmate. It turns out for the particular search we look at here, the math graph implementations give the stronger bounds, but of course they have different analysis implemented, and that's just this particular sector here that it's gives the stronger bounds. What you see here is these are 95% exclusion limits. The lighter one here are 68%. So the red points here are the excluded one. The orange point here somewhat between 68 and 95% excluded, and the green points here, it's very difficult to distinguish the color, sorry, would be allowed. We have here the octet fermion masses, and here we have this Bino-like singlet mass. And we see this is about, for this, for Majorana fermion Cluino here, about 2.3. That's what we also have in supersymmetry for similar scenarios. The color octet has here the Dirac state is G plus, for example, similar to G0, has larger bounds, the stronger bounds, the reason being its cross section is about twice the one of the Majorana fermion here. And if you sum all 5 states here, you get here bounds of the order of 2.7, 2.8 TeV. This would be a decay chain via the triplet BNGB. Of course, could also be that you have a decay into the octet. For example, you would have this Greeno-like state into the color octet BNGB plus this Bino-like state. And also here, you can do the same business. The important point is you can get, in cases where this Bino-like state is massless, where, for example, you would have, instead of the Bino, the neutrino, bounds of a few up to 2.5 here, 2.3. Here you can get up to close to 2.7, 2.8 TeV if you sum over all states. So that's, from this point of view, this sector is already very much constrained. But this would also tell us that the color triplets, where we have bounds from the LHC from individual searches, which are order of 1.4, would have to be expected in these models in the order of 3 TeV. That's good. This already brings me to my conclusion. Composite Higgs models provide a viable solution to the hierarchy problem, because this Higgs is not a fundamental scalar, but a mixture between a bound state and a composite state, up to the number Goldstone bosons. Generically, one has several BNGBs, not really Higgs, like it's in the minimal model. We have fermionic bound states, which are not only color triplets, but it could also be color octets, they could be color singlets. This gives rise to a very different phenomenology than is usually started in composite Higgs models. In this particular M5 model, under very specific assumptions, we find that the color octets are bounded in the order of 2.8 TeV. Things will be different once we relax these assumptions. As an outline here, what we do is we also look into different scenarios. There's a funny things like this 5-3 charge could, for example, decay into a doubly charged pseudo-number Goldstone boson. It would be like a doubly charged Higgs boson, an anti-B quark. And then you would have 2 Ws and a B quark as a final state from this decay. So you would have to look for the LHC for 4 Ws and 2 B jets and things like that. Investigating this, thanks for your attention.
Okay, so are there any questions? Yes, please.
beyond the fact to explain the hierarchy problem, to solve the hierarchy problem, there is some deviation of the standard model from measurement, like the one which were said about the B decay and by the seminar yesterday to motivate this extension. Because in my idea, the first thing to modify the standard model should be to explain something which is not in experimental agreement with the standard model.
We agree with this statement, yes. Actually, you can build composite Higgs models which can give you laptop quarks, which still conserve, which don't allow for proton decay, which can explain, for example, the B anomalies. That's possible. You would have as a global group, for example, you would have a gauge group, if we recall it correctly, SU10 models, and there's a global symmetry, something like SU9, SU8. I would have to look it up in the literature. But there are explicit models which address those issues as well.
Just to, because I'm not from the beginning, as far as I understand, composite models suffer, I don't know what kind of UV completion. They have not been able to find the constituents in a UV complete theory. And apparently they follow, I mean, this a kind of a bottom-up approach to top-down approach, which is the previous studies with similar aspects of technicolor theories. And can you comment on that? I don't see how you, what are the constituents to call something a composite Higgs boson?
I don't have an explicit representation here, which would really be a full UV completion. I know there has been this paper by Sanino and Giacomo Cacciapaglia, where they tried to really get a UV completion, having some supersymmetric models at the gut scale. There's an additional scale that generates dimension 6 operators.
Okay, maybe because time is passing, so just the last question.
I was wanting to come back to the first question you got. Actually, the kind of discrepancies which would worry me much more is, you know, the mass of the predicted age from all the low energy measurements was 90 GeVs or something like that, and it was found notably higher. And I don't think there has been any change recently in those measurements. And I'm not under the impression that what you have introduced in this composite scheme would resolve this discrepancy. Or are there some, because it's so well hidden that I would be surprised it resolved this discrepancy, but maybe you can comment.
So if I understand your question correctly, you refer to electroweak precision data and the global fits to the standard model with and without the Higgs boson. In case there's no Higgs boson included, as I say, the prediction would be order 90 GeV, 95 GeV. We have the standard model Higgs. However, once you include the standard model Higgs, you find within 1 sigma you're consistent with the data. The reason being the dependence on the Higgs boson mass is logarithmically. So it's a rather weak dependence. And if you look at the band that's really flat in Higgs direction, what's more important, for example, is the top quark.
Okay. I think we have to finish the discussion. So let's thank the speaker again. And I don't know if we have the first speaker online already or. Not yet. Okay, so can I ask Francisco Botella to present us the results on the phases of CKM and PMNS in HW model? Yes.
Can you hear me?
It's online. Yes.
Hello.
We lost connection again. Okay. Yes. Welcome, Francisco. Very nice to have you with us. Can you hear us?
Yes, yes. Hello. Can you see the?
Yes, we do see the slides.
You can see me also, no?
Hear you now. Okay, so please go on. The floor is yours. I will just mention when you have 25 minutes for your presentation. I will mention 5 minutes before the end. Okay. Thank you.
Okay, thank you very much. Thank you, the organizer of the Corfu meeting, for inviting me. I'm really sorry, and I regret not to be at Corfu, but it was not my fault. It was a last-minute cancellation of a flight by airlines. So let's go to this relating the phases of CKM and PMNS matrix, and this basis with work with Gustavo and Miguel Nebot in this paper, and also including Joao Alves and Fernando Cornet Gómez in this other paper. I mean, the main goal here is to find a scheme where we found relations between the CP violation in the quark and in the lepton sectors. We must not forget that the CKM is complex, even if we allow the physics, that this complex CKM does not imply necessarily complex Yukawa coupling, can have vacuum-induced CP violation. And in order to relate the CP violation in both quark and lepton sector, we will assume that CP is spontaneously broken. So the first model, let us talk about two Higgs doublet model and spontaneous CP violation. The first model of spontaneous CP violation was introduced by T. 73. It was a two Higgs doublet model with vacuum expectation values with a relative phase which violates T and CP. But note that two Higgs doublet model in general has a scalar favor change in neutral current at the level that can be eliminated by natural Freiburg conservation at the Glasshow, at la Glasshow and Weinberg with a Z2 symmetry, Freiburg blind. Or they can be, this scalar Freiburg change in neutral current can be controlled with minimal Freiburg violation in models like the BGL models. But if you ask for a spontaneous CP violation, natural Freiburg conservation, it turns out, Gustavo Branco showed a long time ago, that it generates a real CKM. And if you go to the other BGL models, it turns out they cannot have a spontaneous CP violation. This set for symmetry is too strong constraint. Nevertheless, if we keep a set to softly broken, in the Higgs sector, it allows for a spontaneous CP violation. And then some particular realization that we previously developed of the Z dot that we will, I mean, this realization will define what we call generalized BGL models. And as you see, the scalar field has the standard transformation on the right-handed part, but the transformation, the double left-handed are flavor dependent. Then this does not meet the natural flavor conservation criteria, and it will generate a complex CKM. So let us remind the model, I mean, the generalized BGL model, and develop with a spontaneous CP violation. So we introduce also, I mean, the model usual, the two Higgs double model here in the quark sector, and here is in the lepton sector. We have introduced neutrino right-handed just Dirac for simplicity. There is work in progress for Majorana case. So the model, the JPGL model defined by this previous symmetry, it turns out that these gamma 1 matrices, the couplings to the 5-1, has this particular form, all these zeros, and the couplings to the gamma 2 have only coupling to this. This is the space because the first doublet is special properties. We call that this is generalized BGL because BGL models, for example, for the down couplings, I mean this and this, has this structure, for example, and the ups couplings has CDR structure, but with a 0 here and the 0 here and the 0 here and the 0 here. So you can realize why this is a generalization. Don't forget that, I mean, these couplings can be viewed as projected, something projected by the P3 projector, this guy, and the other by 1 minus this other guy. Both the spontaneous symmetry breaking and spontaneous CPR violation are triggered by the vacuum expectation values of these guys, and particularly the spontaneous CP violation is triggered by the relative phase among these. So if we go as usual to the Higgs bases, we write again the Lagrangian in this way. There's the coupling to the H1, the one that has no vacuum expectation value, and the has vacuum expectation value will be the so-called mass matrix. And then they will be the new couplings we have here. It is important to realize that the masses is the sum of the two pieces. And here is the relative phase. And this has only pieces in the third row. And the same here, and the same here, and the same here for down, up, electron, and neutrino. And another important result is that I will not explain, but it's trivial because this is particular structure, is that N has this structure. This is proportional to the mass matrix, and the proportionality is another matrix that is diagonal, but not being unitary. I mean, if you diagonalize this, you will not diagonalize this. So in F control, the scalar flavor change in neutral couplings in general present in all sectors and in the couplings to H2. The Higgs potential finally, as I said, was a Z2 symmetry with the softly breaking term. So with these two pieces, even if everything is real, you can have vacuum expectation value, and the relative phase is fixed by that. So let us see how appears CP violation in this model in the CKM and PMNS. I mean, from the structure of the mass matrix, the phase is in the third row. So it's trivial that the mass matrix has a real, something real times this structure, where this is plus or minus theta, if you go up, down, etc. Electron neutrino. So to bidiagonalize this, we must have a unitary matrix here and here, but on the left, it's enough to have this structure. I mean, to cancel this piece. And the rest is the diagonalization of a real matrix that can be done with two orthogonal real matrices. So that means that the only relevant thing is this, the left-handed rotations, because VCKM is this piece and this piece, I mean, it's the usual stuff. And then the VCKM, I mean, here you have one, this phi 3, remember, is this guy, so it's the diagonal with the phase. So from the up sector, you have a minus, and then you have this phi 3 theta, and from the others, you have phi 3 theta, so you have phi 3 2 theta, and this is the structure of the VCKM. A rotation, a diagonal with a phase, the vacuum phase, in twice the vacuum phase in the diagonal and a rotation. The same in PMNS. So this rotation in general 3 and 3 parameters, 6 and 1 and 7 with 7 parameters, we can have arbitrary V and U. In fact, we have too many, except that CP violation in the quartz sector and CP violation in the lepton sector must vanish with theta going to 0 in both cases. So it is interesting to scrutinize the relation between the PMNS phase and the CKM phase. To present the relation, I mean, the simplest approach would be to impose the absence of a scalar fiber change in neutral couplings, because there is no experimental evidence about this. But this leads, as we will see, to a real CKM, and that is a scalar fiber change in neutral coupling unnecessary. This is the same as the Gustavo general argument that I showed at the beginning. So with natural flavor conservation. So the scalar flavor change in neutral coupling are encoded. Let us analyze this coupling a little bit more in these matrices that we must diagonalize. We must go to the basis where it's diagonalized. So, I mean, it's clear that the remember that it was like that. So this diagonalizing this, it remains the same. And here you have the transformation of this guy in this way. So it remains that the matrix that controls Freiberg changing neutral couplings is the diagonal of the masses, and it appears here as a projector that is real. And so this projector will control the scalar Freiberg changing neutral coupling. And this projector having this form can be written this way. Okay, so this is P3 is the 001. So this is the third, these guys are the third row of the rotation matrix, and they can be written like that. Okay, so note that this is a unitary vector because it is an orthogonal real matrix, and it requires two independent parameters. But note also, I do not explain that it is written here, and it's straightforward and trivial, that the projectors in the up and the down sector are related by B's. So we only need two parameters to control scalar Freiberg changing neutral couplings in the quark sector in addition to BCKM. Okay, so apparently we have 6 parameters to define the flavor sector. Now about the relation with the elimination of CP violation and elimination of scalar Freiberg changing neutral couplings, it's clear that to eliminate the scalar Freiberg changing neutral coupling, we must have all these guys, all these terms. Look that Freiberg changing is Ij, so there will be in the Ij Freiberg change if there are 2 of these different from 0. So if you put one equal to 0 and the one equal to 1 and the other is equal to 0, you eliminate. It's the only way to eliminate Freiberg changing neutral couplings. This is what is written here. And then this projector is either 1, 0, 0, 0, 1, 0, 0, 0, 1. That means, and it's shown here trivially, that automatically BCKM is real if either PU3 or P2 or PD3, the projector in the up or in the down sector, has this form. Here is shown for the Electron sector, and the idea is that the BCKM or the PMNS matrix turns out to be a real rotation and a diagonal of phases if this guy is of this kind. So in this model, to have CP violation, the CKM matrix, there must be 3-level scalar Freiberg changing neutral couplings, both in the up and in the down sector. And the same applies for the Electron sector. So it's a tremendous connection among CP violation and the presence of scalar Freiberg changing neutral couplings. So that this is a priori great difficulty. So let us see now how the relations, how we can present the relation between the CKM and PMNS in this scheme. So first of all, these are remember the VCKM and PMNS in these parametrizations. They are the usual rotation matrix that you are going to use as usual in a plane, 1, 2, 2, 3, etc. So we can choose, for example, a general rotations for the up part and a general rotation for the down part. Forget about the 0 for a while. And you see 3 and 3, 6 and 1, 7 parameters. So we previously said 6. So, but look, if we choose in this way and this way, that is completely general, this guide in transpose, it comes here. And because this is this is 1, 1 in the sector 1, 2, it goes to the other side. So V depends on this product. At the end, it depends only on the difference of this guy and this guy. So we can always choose this equal to 0. And the number of independent parameters in the quark sector are 6. 6 mixing angles and theta, matching the 4 standard CKM, well known, and the 2 parameters that we showed previously from the scalar Freiberg changing neutral coupling sector, either 2 from one or 1 from one and 1 for the other, etc. The same happens with the Electron sector. So in summary, I mean, the experimental information will constrain VCKM and scalar flavor changing, neutral couplings, and could fix ideally the model parameters, all this. A full analysis was done in this paper. I will show now the results. But the most important aspect here is that ideally one can fix from the quark sector theta with this procedure, since CP violations were established in the quark sector, up to these guys, of course. And finally, with the well-known PMNS mixings, we know 3 angles by sure, together with some information from the scalar flavor changing sector, and incorporating data, we should be able to predict delta, okay? Let us see how it goes, the analysis in the quark sector. In the quark sector, the model is viable after surmounting flavor constraints, heat constraints, electron constraints, and overall that, I mean, the scalar flavor changing neutral coupling constraints, theoretical constraints. I mean, for example, in the RD and RU, the parameters that control the flavor changing, there are 3 area vector of 3 components, and we put here the minimal, the one in the middle, and the maximal. If one in the middle were 0, so the other would be 0, so there will be just a 1 and the other two 0, so this term is excluded. So this is the region that we get, and essentially what tells us that, I mean, there is a minimal amount of flavor changing neutral currents, which you can see because this is this line, and in some sense, maximal this line. Similar things happen in the up sector, more involved because this graph, but anyway. So also, I mean, R11 is the mixing of the 125 GeV Higgs and the Higgs that couples with the standard model couplings to Fermi. Okay, so in this model, there must be R11 and R must be different from 1, and there must be mixing with the, because there is CP violation in the Higgs sector, with the CP odd, I mean, and for example, you have here sine of 2 theta versus R31. And the most remarkable thing is the large, I mean, the enormous variation of sine of 2 theta that we have. Of course, R31 cannot be smaller than this, than something, and maximum values here. So here you have the constraints about tangent beta, and the constraint about tangent beta with R11. And for the sake of what we will do later, I mean, remember that this plot, and you will see that sine of 2 theta is fixed more or less. We will fix it in the upper part, so we will be interested in this region. Okay, so surprisingly, we have a lot of room in the scalar flavor changing neutral coupling sector, and consequently in the theta value. So if we want to show a relation between delta CKM and delta PMNS, it is not the best way to generalize this analysis to the whole, to both sectors. So the idea is going to simplify models in this scheme. And I mean, we know that we cannot eliminate scalar flavor changing neutral couplings, but we can eliminate as much as possible. I mean, and keeping spontaneous, keeping CP violation in the CKM and the PMNS. And this can be fulfilled just imposing a 0 in one of the R's. So we are allowing only, for example, if we choose this structure, we only allow top channel transitions, scalar flavor changing neutral couplings, or top U or CAU, and the same for RD. Okay, so we are going to impose 1 here and 1 here. Okay, so I mean that is following experimental things because we are not seeing these transitions. And because we eliminate one parameter here and another here, they have in the dark sector, this model should incorporate the minimal flavor answer because we are going from 6 to 4, and the 4 are the 4 parameters of the CKM. In fact, they still allow transitions, flavor changing, will be fixed by one of the 3 mixing angles of VCKM. So that's, I mean, very predictive and extremely restrictive. So it's not clear that this is going to be possible. So now that we have in the quartz sector 9 models, if you choose these 3 possibilities times 3 possibilities, you have 9 models, and 9 in the electron sector, and then we have 81 models that has been analyzed. And we have found that only 1 survived experimental data. So the one I present here, the one in the quartz sector has this structure, I mean, DC transitions and DB transitions. And note that if you impose that this is 0, then because this is the 3rd row of the rotation in the up sector, it must be of this kind. And if it must be of this kind, the last rotation must be an R23. And then you can put here an R12 that moves the first 2 lines and nothing else. And the other one, you just can put R13, and of course also an R12 rotation that moves the first 2 lines. But we explained before that you can eliminate this, so there is nothing else. So here you have the 3 parameters, and the theta. So imposing this gives you this VCKM as I promised you. And this is, of course, I mean, minimal freedom violating because these things are controlled by CKM. So the thing now is to refit the standard VCKM with this parametrization. And
we still have 5 minutes.
Okay, thank you. And here is the result of the field. Of course, the angles tends to be, even if you switch, I mean, this is the standard parameterization by switching some of them. I mean, you have the tradition, more or less the same angles that you have in the standard parameterization, and theta is fixed. And the point, especially relevant, is that with this assumption, we have essential, I mean, we have been able really to fix theta. Now that we have RU and RD fixed, I mean, these guys are fixed by these mixing angles, and this is a non-trivial result that this fulfill these constraints, and essentially the points are here and here, and I mean, the implications of this, I mean, in addition to this, it goes always the presence of transitions, top, charm, and BD. So the effects will depend on other parameters, but now if we have fixed sine of theta, to theta, essentially sine of theta is fixed. That's what I told you before. In this case, we are in a line near here 0.9, so R11 is restricted to be between 0.8 and 0.9 or something like that. So we are in this region, and tangent beta is more reduced. So at the end of the day, we have these constraints and these constraints. And then if you calculate the branching ratio of T to charm Higgs, you have the flavor changing structure, the intensity that appears in front of the projector before, the necessity of having mixing, deviating this from 1, and you get this very, this very sharp prediction that is a factor of 2 below the actual upper bound, as I showed yesterday in one of the talks. In the electron sector, now, the mu and gamma will be controlled by combinations of these if we allow presence of these transitions. And then, in the Tulip-Barthy graphs, it turns that we need, fine-tuning at the 10 to the -4 and 10 to the -5 among different contributions. So it is mandatory to kill these transitions, not to have flavor changing between mu and E. So we must put a 0 here or a 0 here. So instead of 3, we have 2 possibilities in the charged lepton, and the neutrino sector we have 3, so still we have 6. And out of the 6, the only one that is allowed experimentally has this structure. So again, it is trivial that if you have this, the last rotation must be for 1, 3 and 1, 2, you can put. And this is a little bit tricky because the only we have here about this kind of rotation is the rotation 1, 2, so we must put the permutation here of the second and third line. But this trivially is a rotation times a diagonal 1, 1, minus 1. So in this case, here is the PMNS matrix, and then fixing 2 theta that we have extracted from the electron sector, and using just the, see, we conserve the mixing of the PMNS, we don't use the knowledge that people have about delta L. I mean, we have 2 solutions, both with the same scalar favorable change in neutral couplings, and both with different Jalskog invariant. So you have here that both solutions, in one of solutions, the standard delta PMNS, the phase, the standard parameterization, that we, in this case, we predict completely is 293 degrees, they were more favored. And there is another solution on 126 that is less favored by the actual knowledge. Okay, so using the information on CP violation in the quark sector, we have been able to predict the phase of PMNS using the connection that the spontaneous CP violation provides in this model, in particular this solution. Note that we also have the parameters that control scalar favorable change in neutral couplings. The structure was this, so we have tau E transition, so we will have the Higgs going to electron tau. So in this case, here is the prediction with the flavor changing terms, and when you plug in everything, all you know, I mean, the region of this and this, you get this even much more sharp predictions that this is, I mean, between 5 10 to the minus 3 and then 3 10 to the minus 3. To my knowledge, publishes this bound, but CMS has announced this bound. Still, I mean, it would be, but still you have this factor, so this should be, in any case, should be seen clearly or disprove. Nevertheless, I mean, take this as a way that we have simplified, and in this way we can explain that, I mean, we can predict this delta PMNS from the quark sector, but it's very tightly to these other predictions, okay? So let's go to the conclusion. We have discussed the possibility of having a framework where there is a connection between CP violation and the quark and electron sector. We have used a 2 Higgs double model with a spontaneous CP violation that is in the framework of the so-called generalized BGL. We have that they realize with a particular symmetry, is a particular not flavor blind set to symmetry. We have shown that in order to generate a complex CKM, one has to have a scalar favorable change in neutral coupling both in the up and the down sector, and similar in the electron sector. It is remarkable that you need a favorable change in neutral coupling also in the neutrino sector, and it cannot be eliminated. You eliminate them, then you get in trouble with mu and gamma. So you must go to one of these 3 models in the neutrino sector. We have shown that within those generalized BGL there is a connection, and the interplay among CP violation, and the existence of scalar favorable change in intercoupling makes this relation quite involved, implying connectional predictions for processes mediated by scalar favorable change in intercurrent in all the sectors, up, down, quark, etc. To clarify all these relations, we have worked a model that has the minimal amount of scalar favorable change in neutral coupling needed to keep spontaneous CP violation, to keep CP violation transmitted to the CKM, the spontaneous CP violation transmitted to the CKM. These simplified models verified the minimum flavor answer, and they were 81 models. In the model, we found, out of these 81, we found 1 model that is in agreement with all the constraints. And the connection between CKM and PMNS give a prediction of PMNS in agreement with recent PMNS analysis, with the recent tendencies together. And this is the way, in this case, in this simplification, we can say clearly, I mean, together these predictions here. Okay, and that's all.
Okay, thank you very much. That was a very interesting presentation. So I think we all the time. Okay, we
why you did not study the PMNS matrix in the framework of the CSIC model, which is the only model which accounts for the very small mass of neutrinos?
So, sorry, can you repeat? I didn't hear at the beginning. Franco, can you repeat? I cannot hear.
No, my question is this. Why you did not study the PMNS matrix in the framework of the CSIC model, which accounts for the very small mass of neutrinos?
I told you that Majorana case is under study. So, I mean, we have other problems to solve, how to show the connection. So that we, in fact, we have some results related to CISO, but this will come next month.
A question which is, I take off the mask. Okay. A question which I know arises in left-right models, but it should arise here too. If you have CP symmetry at the Lagrangian level, then you can impose theta in front of GG tilde equals 0.
Mm-hmm.
That means after that, you can calculate theta.
Yeah.
You can calculate the amount of contribution to the EDM. I know in left-right model it tends to be too large. So I was wondering here.
Okay, let me tell you, I mean, in principle, theta is here is 0 at the level, and you can calculate. This was not, the model was not designed to solve the strong CP problem, okay? So, for example, in these graphics that I have not explained to you, there is some red color. So this red, are you seeing the screen?
Yes.
Okay, so these red colors means the regions where, I mean, we calculated that one loop, and the regions where you can fine tune the model. But this has been done only in the case of the Electron Sector in the general case, okay? So, but of course, I mean, this has not been designed to solve the strong CP problem. I mean, it solves partially in the sense that theta at the level is 0, but you calculate one loop. We calculated in this model, and I mean, you have to you have to fine tune, and you have regions where to fine tune. That's the only thing I can say about that.
Oh, okay, thank you very much. I'm afraid we don't have time for more questions. So thanks, Francisco again. Thank you very much.
Okay. See you. Bye-bye.
Another Zoom speaker waiting. It's Paul Asmuss from Daisy. Are you with us?
Yes.
Yeah, okay, so welcome at Corfu. And Paul is going to report to us about the Higgs studies in Atlas and CMS. So you have 25 minutes for your presentation. Please share your screen. Yes, we can see your slides. We can hear you. So please go on.
Okay, great. So I guess you also can see the slides in full screen. And yeah, then thank you very much for giving me the opportunity to present today the Higgs studies at both Atlas and CMS. And so as a pre-remark, let's briefly talk about the standard model Higgs boson and how it was discovered. So, I mean, you are most likely aware that the standard model of particle physics is remarkably successful in both describing and predicting experimental results. And it was completed by the discovery of the Higgs boson in 2012. On the right-hand side, you see one of the two discovery channels, the diphoton channel, with the full run-2 Atlas dataset. And you see why this channel is so liked, because you have a rather small background and this nice and clear Higgs peak above that. So far, the main production and decay modes of the Higgs boson have been observed, and we have, since the discovery, entered the era of precision measurements, for example, for the Higgs potential and targeting rare decays. Despite the strong success of the standard model, there is evidence that there must be physics beyond the standard model, BSM physics. For example, in the standard model, we don't have an explanation for neutrino masses, and there is no candidate particle for dark matter. So today I'm going to give an overview on recently published Atlas and CMS results, targeting standard model and BSM physics alike, and all of these analyses are based on the full LHC run-2 dataset. So as I mentioned, I will also cover BSM physics, and for many BSM processes, the Higgs boson or Higgs bosons play a crucial role. For example, there can be additional Higgs bosons in enlarged Higgs sectors. There can be invisible decays of the Higgs boson, for example, to dark matter candidates, and there can be contradicting properties of the 125 GeV boson, contradicting the standard model predictions, for example, CP violation or changed cross sections and branching fractions. But before talking about BSM physics, the first analysis I'm going to present today is an Atlas analysis referenced here on the top right, targeting the Higgs boson production cross-section in the Higgs to tau-tau decay, which has the largest leptonic branching fraction with about 6%, and is therefore a unique way to study the Yukawa mechanism. The measurement is, however, complicated by the presence of neutrinos in the tau lepton decay, and the main background in this search is from the Z2 tau-tau decays as well as TT bar. This analysis uses the simplified template cross-section framework, STXS, in the stage 1.2 with a reduced set of bins. And the target of this framework is to maximize sensitivity by minimizing the theory dependence. And the bins in this framework are defined to enrich events of a certain production mode. And this you can see here on the right in the schematic, where you have the production modes on the left, the STXS bins in the center, and the analysis categories on the right. And these analysis categories are defined based on the STXS bins targeting the individual production mechanisms. Recently added are the TTH and VH categories, and the events of a certain production modes in this category are enhanced using multivariate techniques. The Z2 tau background is constrained by both simulations and data in control regions, where the control regions are defined orthogonal to the signal region, selecting Z2 lepton plus additional jet events with a dilepton mass above 80 GeV, leading to over 99% purity. And this is used to emulate the Z2 tau-tau by using the embedding technique. And additional weights from simulation are used to account for kinematic bias, normalization effects, lepton triggers, identification and reconstruction efficiency. And all of this considers also the lepton isolation. And here on the right-hand side, you see the effect of this embedding technique, where on the left, you have the Z2 lepton, and in green, you see the result for the Z2 tau-tau using the technique where one of the leptons in the Z decay is replaced by a simulated tau. And you see that it agrees well with direct Z2 tau-tau simulation. This technique is validated also using simulated samples for all background processes, while the top right plot is a combination of several selection categories. On the bottom left, you see one of the distribution for the vector boson fusion production in the tau leptonic, tau hadronic final state. And the observed discrepancies agree well with reported Z plus jet measurements. With this analysis, the total proton to Higgs to tau-tau cross-section can be measured, and the result is consistent with the standard model prediction within uncertainties. And it is also measured per production mode, which you see here on the top left, as well as the combination on the bottom with respect to the standard model prediction. And the overall compatibility with the standard model is 88%. With this result, also the observation of the vector boson fusion production mode with a significance of 5.3 sigma can be constituted, as well as evidence for the gluon-gluon fusion with about 4 sigma. The cross-sections are also measured in terms of the reduced set of bins of the stage 1.2 of the STXS, showing good precision up to 24% in this bin here in the VH and VBF production mode with a large digit mass. And this is as well in agreement with the standard model predictions. The second analysis I'm going to show to you today is also targeting the Higgs to tau-tau decay, but mainly analyzing the CP structure of the Yukawa coupling. As in the standard model, the Higgs boson is predicted to be CP even, so a scalar, and any kind of deviation from this would immediately indicate new physics. A fully CP odd, so pseudoscalar, is already excluded, as well as CP violation in a coupling to the vector bosons. For this analysis, the H-tau-tau couplings are decomposed into CP even and odd parts indicated by these kappa parameters. And then the effective mixing angle phi tau-tau is defined through its tangent as the ratio of these parameters. And you see its effect in the top right plot by a shift in the phi CP distribution, which is the angle between the tau decay planes. This phi tau-tau angle is quite important, as a value of 0 would correspond to a pure scalar coupling. And for example, the next to minimal supersymmetric standard model allows a value up to 27 degrees. Also, other BSM models predict non-zero values. The analysis here includes fully hadronic final states from the tau decay, as well as tau H, tau mu final states. As in the previously shown analysis, the Z2 tau-tau contribution is estimated using an embedding method based on Z2 mu mu decays, and the backgrounds with jets misidentified as tau leptons is determined from data by selecting tau hadronic candidates in regions where there shouldn't be any tau leptons. And 2 MVA discriminants are used to separate signal from major backgrounds in the tau H and tau H tau mu final states. And these have 3 classes each: the signal category, the Higgs category, and 2 background categories targeting genuine taus and jet fakes. On the bottom left, you see the genuine tau category, the background category in the tau mu tau H final state after the MVA-based selection. And on the right-hand side, you see the signal category in the same final state, where in each of these windows of increasing BDT score, you see the phi CP distribution, and you see that the MVA technique is really quite powerful in both discriminating CP even and odd contributions, as well as, as you see on the bottom, increasing the signal contributions. The final result of this allows to distinguish CP even and odd couplings with a significance above 3 sigma. And the result observed is, as you see here on the top, compatible with the standard model prediction within the uncertainties. And as a cross-check, also the Higgs production signal strength modifier mu tau tau, as you see on the top right here, has been calculated. And the observed value of 0.8 is also consistent with the standard model within uncertainties, where the red star here indicates the standard model prediction. So from the standard model going to rare decays of the Higgs boson, this search here targets invisible decays of the Higgs boson, where the invisible decay products could also target a dark matter candidate being the mediator. And the search for weakly interacting massive particles, WIMPs, indicated as chi in these Feynman diagrams here, relies on the associated production with Z boson to search for missing transverse energy. Furthermore, the Z boson is required to decay leptonically for a clean signature. Since dark matter must be massive, there's a strong argument to be made to look for it in interactions with the Higgs sector. And in this analysis, there are several benchmark models targeted. First, the decay of the standard model like Higgs boson. Second, a simplified S-channel dark matter production, for example, here. And third, 2x doublet model with additional pseudoscalar models, so here and here on the right. The interpretation of the limits from the first 2 of these are then compared with direct dark matter detection experiments. So dominant background contributions for this search originate from vector boson production as well as some non-resonant WW or TT bar contributions. And then there are smaller contributions that are labeled other. In the plot here on the right-hand side, this other is not listed because it's negligible in the signal region. So the background prediction is compared to, the data is compared to the background prediction and the signal hypothesis in a simultaneous fit of the signal region, as you see here, which you see here on the right, and control regions. And the Higgs to invisible sensitivity is increased by using a BDT, a boosted decision tree, providing one single output variable. And this is used in the EMU control region, as well as the signal region, which is shown in the plot for the final likelihood. And you see that the signal hypothesis the contribution is indeed increased with increasing BDT score. So far, the data is in good agreement with the expectation, and the best fit constrains the branching fraction of the Higgs to invisible to be below 18%, which is also the expectation. And the improvements made in this new analysis lead to expected limits, so sensitivities, 45% better than the projection of previous techniques scaled to the full run-2 luminosity. So this is quite the huge achievement. And these results can also be transferred using the Higgs portal model to compare with direct dark matter detection experiments, which you see in red and blue here in the plot on the bottom right. And you see that it's quite compatible with direct searches. The interpretation of results is also done in terms of the 2Higgs doublet model plus additional pseudoscalar, as you see in the top right plot, in terms of the value of tangent beta, which is the ratio of the vacuum expectation value of the 2 Higgs doublets, as well as the pseudoscalar mass MA. And you see the significant improvement with respect to the yellow 2016 result, also helped by the inclusion of the BB-initiated production. The dark matter results are compared to direct searches, as you saw on the previous slide, using, for consistency reasons, the 90% confidence level. But keep in mind that the translation is always a result of some models, so making assumptions, in this case that the decay is kinematically allowed and that the WIMP is a scalar or Majorana fermion. So these results are model dependent. You can also assume simpler, more basic models, and the respective limits are shown here on the top right. And again, you see the significant improvement with respect to 2016 results in yellow. Overall, as just mentioned, there are significant improvements based on the new analysis techniques compared to the previous results, and the dark matter results are competitive with direct searches. The next big block I'm going to talk about is the search for di-Higgs production. Today, I'm going to focus on recent results of the searches in the 4B and BB tau tau final states, referenced here again on the top right. There are, however, lots of additional analyses that I cannot discuss today, and they are referenced here in the orange box. So the 4B final state has the advantage of featuring the largest branching fraction with about 34%, and the search is conducted in for the non-resonant production in the resolved and boosted channels, targeting different production modes. And the boosted analysis is the first one to use the particle net algorithm to identify the BB bar merge jets versus standard model background, for example, TT bar. And the BB tau tau analysis is done in the resonant for the non-resonant and non-resonant production, targeting both of the gluon-gluon fusion and vector boson fusion production modes. And it features the best expected limit to date, profiting from a reasonable branching fraction and a rather low background. The vector boson fusion is quite important as it allows to assess the VVHH coupling here on the bottom right, as well as the VVH, in addition to the tri-Higgs coupling. And in the standard model, there are large cancellations between the tri-Higgs coupling and the box diagram, the two left diagrams, as well as the VVH and the VVH here, second from right, and VVHH diagrams. These cancellations are not present in some BSM theories, so there's quite a discriminating power. And also the tri-Higgs coupling is a critical input to the standard model as it tests the Higgs potential, and this has implications on the vacuum stability. First, discussing the 4B analysis. In the resolved channel, there's a large multi-jet background from QCD and TT bar, and this is estimated from a control region. And both the control and signal region are split into 3 and 4B categories based on the deep jet algorithm. And the background in the 4B signal region, which you see here in the plot, is modeled from the 3B signal region with a transfer factor, which is determined from the respective control regions. The differences in observables are then modeled based on a boosted decision tree, which is trained in the control region separately for both different production modes. As you see, so far for the vector boson fusion selection, the background describes the data quite well. And you see the signal hypotheses here on the bottom, enlarged by significant factors to make them visible. And on the bottom, you see the boosted analysis where the particle net, a jet substructure algorithm based on a graph neural network is used. And it's also used for the jet mass regression. The background in the signal region is estimated from a simultaneous fit with control regions, where the transfer factor is calculated in sidebands of the subleading jet above or below the Higgs boson mass and validated in sidebands of the leading jet with the signal region masked. In the plot on the left, you see the medium purity signal region, which means that both leading jets must pass the medium working point of the particle net algorithm with these selection efficiencies. And again, you can see that the background hypothesis describes the data rather well. On this slide, you see the results for the 4B analyses. So far, no evidence for signal is observed, and the searches are mostly limited by statistics. For the resolved analysis, you see the result here, where the limits above the pink theoretical prediction are still allowed. And this leads to the ranges of the kappa parameters you see here. And in terms of the standard model, assuming that this is what we are looking for, the gluon-gluon fusion production cross-section is constrained to be below 3.6 times the standard model prediction, which is a very, very low value already. For the vector boson fusion, this value is about 226 times the standard model prediction. In the boosted analysis, similar limits can be calculated. Again, the part above the red line is still allowed. And the observation here excludes a value of kappa 2V equaling 0 at 95% for all remaining allowed values of kappa V. And you can see limits in terms of both of these parameters here on the right-hand side, where the part between the bands is still allowed, and the red diamond is the standard model prediction. And the small dotted lines are respective vector boson fusion production cross-sections. In the BB tau tau final state, there are final states allowed that include at least one hadronically decaying tau, and there are 3 signal regions based on different triggers. MVA discriminants are used to distinguish signal and background, and the same inputs are used for the resonant and non-resonant production, where backgrounds with true taus are simulated, and from fake taus, there are data-driven methods, and a dedicated control region is used for the normalization of the Z plus heavy flavor jet background. And in a non-resonant analysis, standard model kinematics are assumed, while the resonant analysis targets a narrow width scalar with a mass of 251 to 1600 GeV. On the right-hand plot, you see the signal region in the tau H final state, assuming a 500 GeV new particle. And you see on the x-axis the parameterized neural network score, and again, it increases the signal content for larger masses, larger scores, sorry. And the largest excess is seen about at 1 TeV with 3 and 2 sigma local and global excess respectively. And the non-resonant di-Higgs production limits the cross-section to below 4.7 times the standard model prediction, which you see here, and other analyses are referenced here also in the summary plot. This is the best expected limit, so the highest sensitivity to date. Coming to a diphoton search, so looking for new diphoton resonances is making use of the clean signature in that channel. Remember, it was one of the Higgs boson discovery channels. So it allows for precise reconstruction to separate standard model background from a potential signal. The interpretation is then done in 2 different models based on a common event selection. So it's searching in this diphoton channel for a new spin 0 state X which is predicted by many models with an extended Higgs sector, or spin2 graviton, in this case, the RS1 model. The largest background for this search is non-resonant diphoton production with smaller contributions, including jets, and the relative contributions are estimated at two-dimensional sideband method based on passing or failing of the photons of the tight photon identification and some isolation criteria. And you see this here in the right-hand plot, where you see the individual contributions, and in black you have the data. The analytic form of the background is fitted in diphoton simulation and photon jet events from a control region, performing the fit above 150 GeV to allow for enough events in the sideband. And the upper edge of the fit here is determined by having enough events for a stable fit. And you see that this leads to a quite spiky background, let's say. And this is smoothened to mitigate the impact of statistical fluctuations due to limited number of generated Monte Carlo events. And the smoothing is based on the functional form determined in simulation and the spurious signal, which is the signal yield fitted in pseudo experiments. And the smoothing techniques leads, as you see here, to smaller and fewer fluctuation, yielding an improved, up to 28% improved actually, limit on the cross-section times branching fraction. The data overall is well described by the background only fit, which you see on the bottom left plot. And the excess with the largest local significance is at 684 GeV with about 3.3 sigma. And global significance, depending on the model, is about 1.3 or 3.6 sigma. So the observed limits, which you see in the right-hand plot, agree well with the expectation. And in the RS1 model, the graviton mass can be excluded below 2.2 TeV, larger, however, for different choices of the coupling strength. And in all cases, a narrow width approximation is used. And a fiducial cross-section is also used, which is the overall cross-section times the acceptance, where the acceptance closely follows the selection criteria. So the last analysis I'm going to present today is a search for additional neutral Higgs bosons. In this case, a heavy neutral Higgs boson capital H here in the center, decaying into the 125 GeV boson small h, and an additional state HS, assuming that this decay is kinematically allowed, and that the subsequent decays are into a pair of tau leptons and B quarks. Such a Higgs sector is, for example, predicted in the NMSSM, where we have an additional Higgs doublet plus an additional singlet, leading to 7 physical Higgs bosons, which you see here on the right-hand side, where these 3 neutral CP even states are targeted in this analysis. And the HS state is assumed to have significant mixtures from the singlet, and therefore suppressed couplings to standard model particles, and therefore the preferred production is in the decay of the capital H. This is the first search of this kind of signature at the Large Hadron Collider. In order to select an event, it is required to have a di-tau mass close to 125 GeV, and the tau leptons must have opposite signs. The BB mass ranges from 60 to 2800 GeV, and the tau final states must include 1 hadronically decaying tau. All of the tau leptons are identified by the deep tau algorithm. And furthermore, at least 1 B-jet is required to be present, selected by the deep jet algorithm. Several neural networks are then used to assign an event to the signal region or a control region for certain regions of the Higgs bosons. And different background estimation procedures are used depending on the final state. On the bottom, you see on the left-hand side the di-tau background, and on the right-hand side, the signal region, both in the tau E, tau H final state. And you see that with increasing neural network output, the respective contribution of background or signal is increased significantly, in this case for this particular combination of Higgs boson masses. As no deviation from the standard model is observed, model-independent limits are determined and combined for all the 3 final states. For capital H masses reaching from 240 to 3000 GeV, where only this lowest limit is unscaled, and the others are offset by respective factors to make them distinguishable. The limits range from 125 down to 2.7 femtobarn for various combinations of the Higgs bosons. And these limits can be interpreted in terms of the next to minimum supersymmetric standard model, as you see on the left-hand side. And the mass region excluded here on the bottom is based on the maximally allowed cross-section times branching fraction of the model. And this red area is where the decay would be kinematically forbidden. So this brings me to my summary. I presented various analyses targeting Higgs physics within and beyond the standard model. So far, all results agree well with the standard model predictions within their uncertainty. However, there are additional exciting analyses to be published rather soon, especially lots of run-2 BSM results are still to come, and significant improvement in statistical precision is assumed to rise with the upcoming LHC run-3 and the high luminosity LHC. Thank you very much.
You can hear us? Can you hear us, Paul?
Ah, yeah, now I can hear you again.
It
was okay. Very silent in between.
On slide 16, I have a question. Yeah, I mean, this is in the future, of course. Now you're still looking for Higgs production and to pose some limits on standard model predictions. But I'm wondering, I mean, if you're looking at this tau final state, so this is the channel where you also showed results for probing the CP properties, right? So at some point, if you include resonances, you have every resonance going to two scalars. It would be interesting to see whether one can use similar techniques then to determine the CP properties of the scalars. So let's say retest the CP properties of this 125, for example, in this scenario. So do you know of any efforts in this direction to extend the single Higgs production to tau CP tests to Higgs production?
I'm not sure, I have to say. I think so far the main focus is to, well, observe Higgs production. But I'm quite sure that as soon as this is done, also further precision measurements will be conducted. And then the tau channel is definitely one of the best channels to do that.
I have a question concerning CP violation in H into tau plus tau minus. You said that pseudoscalar coupling is excluded, and yeah, based on measurement of the angular distribution of planes, decay planes, right, of those stuff. I believe you could limit quantity that is a genuine measure of CP violation, that is a product of scalar and pseudoscalar coupling. That could be just a number that you could get from your data, I believe.
So, well, from this analysis, yeah, it would be, I mean, the result here is...
Yeah, here you say that it's consistent with standard model, which means that this product is limited, and that could be useful. Instead of excluding extreme cases, right, like pseudoscale.
Yeah, of course. I mean, it can be that at some point, I mean, this is the target of this analysis, right? It targets to either say, okay, we can say we have a totally scalar coupling, or we have some admixtures. If we find some admixtures of pseudoscalar coupling, then we have we have some beyond the standard model physics.
I also have a question related to this slide. So probably it is written, but it's really very tiny. What is the uncertainty of the mixing angle that you measured?
Oh, sorry, yeah. This is, so the observed result is 4 plus minus 17, and the expectation is 0 plus minus 23.
Thank you.
Okay, so I think we have to go on. So let's thank the speaker once again. Thank you for joining us, Paul. And now the last contribution in this session is by Ivanka Bozovic from University of Belgrade, and who will present us these results on the linear E plus E minus Higgs factories. So, you will get help from. Go ahead.
Thank you. Thank you.
Okay, so you have 25 minutes. Please.
Okay, thank you very much. I think it's a really great luck that we had previous speakers talking on mainly Higgs physics at Atlas and CMS. Because I'm going to introduce future linear colliders as options for Higgs factories that basically can do the same, but hopefully better. Should I stop talking? No problem. Can I continue? Thank you. So, I mean, most of the people here are theorists, so probably I do not have to explain very much why do we need Higgs factories, but I will nevertheless introduce linear collider projects as a possible options, talking a bit on their detector concepts and technologies and what can be measured in the Higgs sector with these devices. Okay, because I'm experimentalist, I have naturally my favorite theorist, which is Nima Arkani-Hamed, which I robbed by a few slides. As already said in the previous talk, Higgs discovery ended era of reductionism and symmetry in particle physics. So we observed a unique particle, never seen before, fundamental scalar unique in itself couplings, that basically opened two important questions of the nature of the relativistic vacuum. How can we accommodate it in the observed density of the universe, and why Higgs is not enormously massive or even Planckian? This can be formulated as a well-known cosmological constant and hierarchy problem, where Nima is here asking even more liberally formulated question: why is there a macroscopic universe at all? At LHC, we do not have new discoveries, so basically there are only limits improving with every run. And with the current resolution, for instance, to probe Higgs compositeness, the Higgs could be as point-like as elementary as pion. Also, even high luminosity LHC could probe Higgs self-couplings with 50% uncertainty. So being a harbinger of the profound new principles at work in the quantum vacuum, Higgs should be studied more closely. What brings us to the Higgs factories? Higgs factories are prioritized in European particle physics strategy from the last year as the highest priority future initiatives. There are several projects on the market, all offering millions of Higgs bosons. Some are linear, I'm going to focus on linear, ILC and click. Some are circular, CPC and FCCE. All electron-positron colliders comes with a set of advantages, like the initial defined initial state, which means reconstructible events from the first principles, also almost QCD-free environment. And what is a particular feature of a linear colliders is the accessibility of the high center of mass energies above TeV. This brings particular benefits when it comes to the measurement of the Higgs self-couplings and also BSM signatures in the Higgs sector. At E plus E minus machines, high precision measurements will be dominated by statistical uncertainty. It's clear that will be run for statistical precisions. The starting point is 100 times the left luminosities. Of course, circular machines are in favor when it comes to luminosity, while a linear could address the higher center of mass scales. Everybody is asking a question: which one is going to be built, and is the physics performance will be the only one to decide? Of course, it's not like that. It is also the flexibility of the physics span. For instance, great advantage of circular colliders is that they can accommodate protons in their ring, while E plus E minus could also give rise to a gamma-gamma collider. Also, then the flexibility to sudden changes, for instance, unexpected discoveries at the high luminosity LHC, then technological feasibility and cost, and I would say also politics, because building such a machine is has a flavor of supremacy in the field a bit as well. Linear colliders comes as mature technologies with a decade, in case of quick, or even decades behind the ILC of vigorous R&D development. So they're ready to take projects. If we would have a decision to make these machines, they could deliver their first beams already around 2035. They all come at stage and upgradable machines, what basically enables various Higgs production mechanisms to be addressed. Higgs Strahlung at lowest center of mass energy, WW fusion, enabling access to Higgs rare decays, and Higgs double production, enabling measurement of the Higgs self-coupling. This is a nice example comparing Z-pole and treat TeV, how the less precise measurement at higher energy leads to the same precision of observables. So we really can strongly benefit from higher energies. Also from beam polarization, and this is illustration from ILC, that could in addition provide new observable sensitive to B physics, helps to characterize the newly discovered particles and thus discriminate between the BSM models. And due to the chiral nature of WW fusion, you can almost double the luminosity with polarization. There are a few technical benefits. These machines are triggerless, and also the readout could be in the power pulsing mode. ILC is the oldest project, and I could proudly say that I was with the Tesla project, which was a European project of the future linear collider already from 2000. Now it is merged from Japanese, American, and European project, where European Tesla technology developed at DAISY was adopted in 2004 by ICLA. This is a cold superconducting machine. It is staged. Basically, it can run from the Z0 pole and WW threshold for precision electroweak measurements up to where beam polarization is available up to 80% for electrons and 30% for positrons. The footprint for the first phase is 20.5 kilometers, and the site has already been chosen in Japan. It's Kitakami, where again with years of geological and similar surveys. I think the free electron laser, European free electron laser operating now as XFL at DAISY, is basically the largest ever accelerator prototype, where basically the full industrialization of the ILC-like cavities is demonstrated. This is a bit of history of the project, which is now in the phase that international development team is being built in order to prepare a laboratory in Japan. And as I said, it all depends on a political decision to build this machine. What is nice about ILC is that, like LHC, it comes with a set of auxiliary experiments, so which are non-collider experiments to study dark sector in the form of parasitic fixed target or beam dump experiments under the name of ILCX. Two detector options are being developed. One is ILD and the other is all silicon SID. ILD is mother of all detectors because every future E+ E- project would start from ILD and then modified according to its conditions. It is optimized for center of mass energy from the Z0 production up to 1 TeV, and the particle flow is the key word for all these detectors, because only neutral part hadrons are left to less precise hadron colorimeters for determination. Everything else, of course, except for photons, which are detected in the ECAL, comes in combination with the central tracker, leading to the jet resolutions between 3 to 4%, which is really needed to distinguish between Higgs W and Z jets. Another very interesting project, this is hibernated now at the moment by CERN, but unique in its feature to access 3 TeV center of mass energy is CLIC. Differently from ILC, it's a warm machine, so normal conductivity high current drive beam feeds the electromagnetic gradient to the main beam. And in the CLIC test facility at CERN, now operating, it's clear, the ability to reach 100 MeV, megavolts per meter gradients in the main beam cavities is been demonstrated. CLIC detector is again, as I said, started from ILD, but then the central tracker is replaced with silicon, so it's all silicon tracker. It's a bit more compact, again, heavily relying on particle flow calorimetry with the timestamp readout, which is in case of CLIC and not of ILC needed because of the beam-Strahlung interactions that are more pronounced than the higher center of mass energies. This project is also well documented in the yellow reports. The performances of all these detectors are similar. I already mentioned jet resolution, then it is excellent transverse momentum resolution fermions, which is crucial, for instance, in the Higgs-Strahlung for the recoil mass measurement, and again, excellent B-tagging performances. Although these projects will be Higgs factories, it's not only Higgs physics that they will address. So it is top physics from the top quark mass measurement, electroweak couplings up to its CP properties and BSM constraints that could be preferably addressed at low or high center of mass energies. Also BSM physics, which is with the preferred sensitivities at high center of mass energies where it can be searched either directly or indirectly. This is a nice example for a BSM indirect search, where, for instance, at the highest center of mass energies, you can reach the new physics scale at the order of 100 TeV. So these machines are really capable to explore for the large span of energies. In the Higgs sector, where I'm going to focus that, the Higgs couplings are also the basics set of measurements, which can be measured in the either model independent way, which is a unique feature of E+ E- colliders, or in the LHC style kappa framework, or in the EFT approach. While Higgs self-couplings, or the measurement in the Higgs sector to probe either dark matter or BSM in general, as well as CP violation measurements, are preferred at higher center of mass energies. As I said, various Higgs production mechanisms are available. This is the Higgs Strahlung, enabling measurement of in a model-independent way of the ZH cross-section. And most of the Higgs couplings can be determined with a better precision than at high luminosity LHC only from this phase. In WW fusion, you have really enhanced statistics. You can access rare decays. In double Higgs production, lambda can be measured. Linear colliders are benefiting so from the accessibility of the high energy scale, from the polarization, and finally from combination of all these results with the different data polarization and within a staged approach. So even rare decays can be measured. You see that the branching fraction is of order of 2 times 10 to the minus 4 for muons. This is example from ILC of the Higgs to muon coupling, with a final statistical precision of 70%. There are less precise measurements from different data samples, so with different polarization at different energies are combined. This is example of a pseudo experiment where signal is fitted over background, while the statistical precision is extracted from the full distribution of the repeated pseudo experiments. This is a comparison what can be done in terms of Higgs couplings at T plus T minus colliders with the situation at LHC and PP in general, where I emphasize again the high energy benefits I'm going to talk now. Okay, you are all theorists, so I guess that I do not have to spend much time on this slide, how well we need to know Higgs couplings. So basically, electroweak couplings of electroweak bosons are particularly sensitive to BSM contributions, lambda even more, and apparently they have to be known at the percent level. And this can be achieved with already in the first phase of operation in the model-independent way. This is the example from CLIC, and this is the example from ILC, where we see that precision of Higgs couplings to electroweak bosons can be measured below 1% already in the first phase. The situation is similar also with circular colliders, and of course, everything is, these machines are superior in combination with high luminosity LHC. I think this is a clear demonstration of such a synergy of a future E plus E minus machine with high luminosity LHC, where already the first phase leads to a huge improvements of high luminosity LHC accuracies. Here, in the case of CLIC, where you add up all phases in combination with high luminosity LHC, practically most of the couplings can be measured at the Fermi level. Now we come to maybe the most critical measurement, and this is Higgs self-coupling measurement. The previous speaker also discussed it. And it is, of course, quite important to know lambda determining the shape of the Higgs potential, but also receiving eventual contribution from BSM models or being significantly enhanced in the electroweak barrier genesis models and so on. WW fusion, where Higgs decays to a pair of Higgs, is apparently the most sensitive process, and it is clearly illustrated that sensitivity is rising with the center of mass energy. So it is no strange that CLIC actually could be superior by reaching 3 TeV in measuring the Higgs self-coupling below 10%. You see that high luminosity LHC cannot do more, or even high energy, because these measurements are constrained by theoretical uncertainties. What is again a nice feature of linear collider is that you can combine double Higgs production in Higgs Strahlung and WW fusion. So this is Higgs Strahlung, this is WW fusion, and different behavior with respect to the non-standard model contributions helps to resolve ambiguities from interference. Also, what is, again, clear benefit from high center of mass energy, by adding 1 TeV ILC, you get again at the level of 10% in lambda uncertainty. It is also interesting to see here if really lambda strongly deviates from the standard model value, actually linear colliders at high energies are again superior in determination of lambda. Then Higgs could serve as a probe to BSM. One way to look for it is in the EFT approach. Of course, the larger the precision, higher the lambda scale reach. So this is the result from ILC, where new physics scale up to 25 TeV can be probed from EFT fits. Some models which are in principle hardly accessible at high luminosity LHC, and this is deviation expected for the Higgs couplings, can be probed can be interpreted in the EFT framework. This is result from 250 GeV ILC, where most of the models can be discriminated above 5 sigma. Again, if you would combine high luminosity LHC plus high energy phase of ILC with polarized beam, there basically no model is left that cannot be confirmed or ruled out in such a combination. As previous speaker said, there are various ways for BSM to manifest in the Higgs sector. One possibility is that Higgs is composite. This is the high luminosity discovery reach. This is, for instance, the 3 TeV click reach in depending on the parameter assumption. So high scale really can be probed. We see here up to 50 TeV. Also, in many BSM models, Higgs standard model Higgs come with initial scalars that could be light, and this is example of their spectrum from ILC, or that could be heavy singlet state mixed within standard model Higgs with a mixing angle gamma that again click at the highest energy could probe superior in comparison to, for instance, LHC reach. Also, if dark matter is massive, as pointed out also by previous speaker, it will be connected to the standard model particles and also to Higgs that could decay invisibly, and by looking into the recoil mass, that nothing is basically recoiling against the primary Z boson in Higgs Strahlung, you can measure the Higgs invisible branching ratio. This is from ILC, where in the full run, you can access it below 0.5% precision. Also, CP violation, CP symmetry can be violated in the Higgs sector. Higgs can be a mixture of scalar and pseudoscalar states. We saw exclusion of the completely odd CP state, and also uncertainty of 23% from the current CMS measurement in the previous talk. These are projections for future projects. High luminosity LHC could reduce uncertainty to 8%, while ILC can measure it down to 4%, again in the Higgs to tau, which is receiving contributions at a 3 level. So it is the most favorable channel. Again, angles between production or even in the Higgs decays between decay planes can be found to fit psi from the angle between the planes. If such a pseudo experiments are repeated, and this is example from ILC Higgs to tau measurement, the psi can be extracted with this final precision. What is interesting to say is that also Higgs to vector boson vertices can be affected by this type of mixing, and that there is a lot of Higgs production and decay mechanisms to probe it. There is ongoing analysis of the Higgs production in ZZ fusion at ILC, where not only fermionic but bosonic vertices can be probed in terms of CP violation. Of course, everybody likes to compare everything between projects, linear versus circular, lepton versus proton, and so on. So I try to do a fair comparison here, which is again personal view. Precision-wise, the linear circular colliders are comparable when it comes to the Higgs couplings. But due to the high energy excess of the high cross-section production mechanisms, you can measure rare decays at linear collider, you can superiorly measure Higgs self-coupling, and you have enhanced sensitivity to the BSM contributions in the Higgs sector. Great advantage, at the other hand, of the circular machines is the extensibility of the Higgs span. You can insert proton in the same tunnel and boost them to 100 TeV center of mass energies. When it comes to the prediction and future 100 TeV hadron collider, there are a few open issues at the moment, like the accelerator and detector technologies, the huge pileup, which will be of order of 1,000. So one really have to think how to reconstruct events under such experimental conditions, and the control of theoretical uncertainties. You all know this better than me, and I just like to point out that significant amount of work in theory is needed in order to improve PDFs, improve non-perturbative calculations, and so on, needed for instance, FCC HH at the level of 100. So you have to improve the 100 times the current theoretical uncertainties, which is quite demanding and presumably requires years of work on it. I'm coming to my summary. I hopefully convinced you that all future E+ E- projects bring significant added value to the projected high luminosity LHC sensitivities in the Higgs sector. The feature of E+ E- machines is our measurements in a model-independent way, where the highest center of mass energies bring added value in terms of the Higgs self-coupling measurements and sensitivity to the realization of BSM scenarios in the Higgs sector. I have basically two main messages. One is that upgrade is important, that these machines should not serve only at the first stages as a Higgs factories. High center of mass energies are genuine advantages of a linear collider, and basically they are ready to wear projects if there would be a decision to have them. Thank you very much.
Thank you very much for a very interesting presentation and keeping time also very well. So we have time for questions. I'm sure there are some. Okay, so we can start with the online one. Paul, yes, please, Paul.
Yeah, so thanks a lot for this very, very interesting presentation. And coming from the Higgs physics myself, I'm quite interested, of course, in everything that can increase sensitivity there. So perhaps you mentioned it and I didn't get it, but first, how likely are these two ILC and CLIC projects to be realized, and probably also is there kind of a timeline? And second, how is it done with the detectors? This is technical, but I mean, at the circular collider, we have several interaction points, but for a linear collider, I assume there would be only one, right?
Yeah, okay. Let me go to one of my previous slides to answer about the timeline. First of all, thank you very much for your question. So you see, both for CLIC, which is somewhere here, and ILC, which is on the top, we have basically the same timeline, allowing 7 to 9 years for construction after the approval of the experiments. So this sets, I would say, the time scale. About the detectors, as I said, the linear collider detectors have been studied already from the beginning of this century. So behind the ILD, and let me find it, it is here, you have from Tesla TDR, you have already 20 years of vigorous R&D using the existing technologies, prototyping, test beams, and full simulations in the physics studies. So if there is a detector which is very well known and described and also technologically available at the moment, I would say it is ILD detector. But the same is true also for click, that basically modified design according to their experimental conditions and replaced TPC with old silicon tracker. So detectors, I would say, are including the R&D. I didn't give any slides on that, but if you look into the reference, you can find it, because mostly people are theorists, so I really did not want to go into technical details of the test beams and detector performances, but I think they're really ready to go projects. And about the interaction point, I think this is the most critical questions when it comes to linear machines. ILC is currently foreseen to operate in the so-called push-pull mode, where both detector concepts could be run as independent experiments. If it comes to the positive political decision by the Japanese government, I'm sure that if this question will be addressed again, and maybe the answer would not be the same. But this is the current paradigm push-pull.
Ivanka, I have a question concerning ILC.
Okay, sorry.
Is there E minus option still on the table, or it is completely forgotten now for higher energy stage? E minus option.
Yes.
Is it still being considered, or it is?
I would not say it is at the moment on the table, but maybe Philip, you can.
I think it is somehow now being discussed again. I know at the workshop which is coming in October, I think that it was mentioned that there will be a dedicated session where these other options will be discussed.
Yeah.
So it's reconsidered now as we are entering the phase where the project can basically make a large step forward in the near future. All the possible options are being reconsidered now.
Yeah, I agree with that. I mean, there was not a relevant R&D activity up to now, but as Philip pointed out, as ILC is getting more serious, and hopefully it is, then other options are also discussed. Also gamma that I mentioned previously.
Okay, so the last question.
Do other options include backscatter laser beams?
Well, this is what Ivanka mentioned, gamma. I think it's much more difficult. So it was mentioned, but I think it's much more difficult than E minus. I would not be very optimistic, because it requires really large changes to the machine.
I think at this point we see difference between theory and experimentalists. The experimentalists would be tremendously happy P plus E minus is improved. But since your imagination is much more developed, you're already thinking about E minus, gamma. But I believe, as Philip already said, once the ILC got approval, these options will be also discussed for sure.
Okay, so now the very last question.
Yes, on the question of the E minus, historically this has been considered at every E plus E minus collider in the last 50 years. It hasn't actually been done since 1971 at 1.1 GeV. But since there is some interest in bileptons, which decay, have a mass of allegedly a TeV or something like that. That would be ideal so I think it should be reserved certainly if the LHC finds a doubly charged bilepton, then obviously it would be a bilepton factory if you had that sort of thing. So the interest might suddenly increase in the near future, hopefully, or not. But it's certainly of interest.
Of course, thank you so much for your comment. I think that I believe that we have people in our community who are aware of that and who will advocate for that option.
Okay, so let's thank Ivanka for all this of the morning session again. And we now have a coffee break. Thank you very much.